Today we're going to be doing Chapter 13. Chapter 13 is on heat and heat transfer. This is a branch of chemistry that we call thermochemistry, and eventually it's going to expand into a branch of physics called thermodynamics. We're going to start the lecture by talking about heat transfer, but before we can do that, we have to explain some basic definitions. So heat is a form of energy. You may have heard this before, you may not have, but basically whenever heat is generated or produced, that is the result of energy passing from one object to another. So the formal definition of energy is the ability to do work. Work also has a formal definition, and it is the application of a force to move an object over a distance. Or if we were to write that in variable form, work, W, is equal to a force applied to an object over a distance, force times distance. Can't remember what's under my block here. Okay, and that leads us to redefine heat as energy that is exchanged because of a difference in temperature or a change in phase. I'm going to reveal all these boxes because I can't remember what I put in there. Okay. Understanding heat as an exchange of energy opens up a new branch of math, because if heat can exchange between two objects, we are able to measure the heat exchange. And to measure heat, we have to have a unit, right? And that unit is called the calorie, or at least the original unit was called the calorie. A calorie is defined as the amount of heat required to raise 1 gram of water by 1 degree Celsius. Now, this is probably a familiar word to you because we consume calories and that provides energy for our bodies to carry on. However, there's a bit of a difference in the calories that you know of and the calories that chemists use to measure things. So, one capital C calorie is equivalent to 1,000 lowercase c calories that we are going to be using in our examples. So when a chemist refers to a calorie, they mean lowercase c, not the food-based calories. To help you remember that, just think that capital C calorie is the big calorie, and there are 1,000 lowercase calories within the big uppercase calorie. The calorie is kind of an older measurement, and it's not as useful anymore, or not as widely used as it once was. So, and the newer form of it is the joule. Now you can read more about how the calorie was discovered, how the joule came about. There's a guy named James Joule who found all this stuff. That's in the reading. We're just flying over the reading, hitting the important definitions so that we can get to the examples. But anytime you see energy measured, it's probably going to be in joules. This book may use calorie in examples. It may even use capital C calorie to throw you off. But in reality, real people doing chemistry, you're going to see energy measured in joules. Now that we've introduced those definitions and units and building blocks, we can start talking about specific heat capacity. Specific heat capacity is the amount of heat it takes to raise a specific mass of a substance by 1 degrees Celsius. Now, objects heat up at different rates, right? That means they absorb energy, they receive an energy transfer at different rates. You guys probably already know this intuitively. So whenever you put bread in a microwave, it's going to heat up very quickly, where other denser food items are going to heat up slower. If you put plastic in a microwave, which is not a great idea generally, that plastic is going to get hot very quickly and it's going to melt fast. Whereas if you put some glass in the microwave, depending on the type of glass, it'll either heat up quickly but not melt, or it will maintain a touchable, safe temperature while the substance on the glass heats up. That's because different objects have different heat capacities. There is a table on page 392 in the book that lists the heat capacities of different substances that we'll be using in this book. You don't have to memorize all of them. However, there is one important one, and that is the specific heat capacity of water. This is one that the book requires you to memorize, and it's not too difficult a number. It may actually look very familiar to you. It is 4.184 joules per gram times degree Celsius. Those units are kind of weird, but you'll understand why it has those units later. Now that we understand specific heat capacities of objects, we can start measuring the heat transfer between objects. And that measurement of heat transfer is a function of the specific heat capacity. So we're going to move on down here. And I'm actually going to keep that on screen. So on page 393, we are introduced to equation 13.1. I would recommend you memorize this because it'll be helpful. It's also pink, or in a pink block, usually meaning you have to memorize it. We have that Q is equal to M multiplied by C multiplied by delta T. And what this means is the heat, Q, is equal to the mass of a substance M multiplied by the specific heat capacity C. How do I spell? Multiplied further by the change in temperature delta T. Can't enter a delta easily. As change in temperature. So the mass of an object multiplied by the specific heat capacity of an object multiplied by the change in temperature that object undergoes is equal to the heat transfer. Now, delta T, you should remember this symbol delta from previous chapters, but in case you don't, delta just means change in. It's a Greek symbol, and in this case, delta T is going to equal the final temperature, the final temperature of an object minus the initial temperature of an object. This is how we can measure change. And now that we have these equations, we are ready to do example 13.1. So I'm going to keep these on the screen over to the side. So example 13.1 is on page 394 if you'd like to turn there and do the example with me. We are given a 500 gram block of copper that starts out at 51.2 degrees Celsius and cools to room temperature, which is 25 degrees Celsius. We want to find out how much heat did the block of copper lose. So we're given a few things. We're given a mass. This is example 13.1. We're given that the mass of our substance of interest, the copper block, is 500 grams. We're given out a beginning temperature and an ending temperature. Delta T, the beginning temperature, the initial temperature was 51.2. Now we don't have to convert to Kelvin, and we'll understand why in a minute. The ending temperature was 25 degrees Celsius, giving us, I'm sorry, an alarm is going off. Giving us a temperature change of negative 26.2. And we're also given our specific heat capacity, C. Since it's not water, the problem statement is going to always give it to you. And that's going to be 0.386 joules per gram degree Celsius. Now, we want to find Q, the heat transfer, the amount of heat transfer. We need M, which we have, we need C, which we also have, and we need delta T, which we're given. So this is going to be a pretty easy equation. We're just given everything that we need. So Q is going to equal 500 grams multiplied by our specific heat capacity, 0.386, and that is in joules per gram degree Celsius, multiplied by our change in temperature, negative 26.2. Make sure you keep that negative sign because it's going to be important later, and that's in degrees Celsius. Now, the reason why we have weird units for specific heat capacity is to allow these to cancel out and give us only a unit in joules. So now that we've canceled the units, let's multiply these values together. 500 times 0.386 times negative 26.2 is going to give us a heat transfer value of negative 5,056.6. Now, the heat transfer has occurred between the block of copper and the atmosphere, the air around the copper, right? We know that the the copper block cooled down. It went from a high temperature to a low temperature. So it makes sense that our heat transfer is going to be negative because it signifies a heat loss. So don't let the negative answer freak you out. That just gives you an idea of what direction the heat was transferred. It was transferred out of the copper block and into the atmosphere surrounding it. We're going to do another example. I'm going to erase this. This is also within example 13.1. We have an iron horseshoe that weighs 350 grams. And we have a blacksmith heating it up. So he's transferring 59 kilojoules of energy into the horseshoe. 59 kilojoules. Remember, kilo means 1,000, so we're going to go ahead and rewrite this as 59,000 joules. We're also told that the horseshoe started out at a temperature of 22 degrees Celsius. So our T initial was 22 degrees. And since we're not dealing with water, we're dealing with iron, the book is going to give us our specific heat. What's it called? Specific heat transfer? What's this thing called? Specific heat capacity. And that is going to be 0.444 joules per gram degrees Celsius. Now, we have everything we need to solve for the final temperature, because that's what we want to find. We just have to rearrange our equation. So we can break this delta T. Well, before we mess with delta T, let's get it alone. So we can reorganize our equation to isolate delta T, and that's going to give us Q divided by M times C. And now we can split delta T into its components, the final temperature and initial temperature. So we're interested in the final temperature, which means we want to isolate that. And we're going to do that by adding the initial temperature to both sides of the equation, giving us that the final temperature is going to equal this Q over MC plus the initial temperature. And we have all of this. So let's plug it in. Our heat exchange is 59,000 joules. I missed a 0. I'm gonna squeeze it in. And that's going to be divided by the mass, which is 350 grams. Make sure you record your units so we can keep things straight. And that's going to be multiplied by our specific heat capacity of 0.444 joules per gram Celsius. And we're going to add to that our initial temperature of 22 degrees Celsius. Now, in order to add these two things together, they have to have similar units. We can see that these units are going to cancel out, and these are as well. This is going to give us 1 over C, which can simplify to simply degrees Celsius. That means we have like terms. So, doing the math here, 59,000 divided by the quantity 350 times 0.444 plus 22 is going to give us a final temperature of 401.7 degrees Celsius. Now, I kept the precise numbers, so the book has as 402 rounded up. However, even if we did round up to 402, we're still not, we haven't recorded the correct amount of significant figures. The answer that we're interested in is the final temperature. The initial temperature we're given is 22. That is 2 significant figures. And the only way to record 402 degrees Celsius to 2 significant figures is to write it in scientific notation. So, our final answer for this is the final temperature of the horseshoe that the blacksmith has added energy to is 4.1 times 10 to the second power degrees Celsius. And there's another way of writing this. I'm not sure if you guys have ever been introduced to it, but instead of writing times 10 to the negative 2, you can write E. This stands for times 10 and then the 2. These answers are equivalent. So 4.0 times 10 to the, did I say negative earlier? To the 2 power is equivalent to 4.0 e to the 2. That is the same number. If this freaks you out, don't use it. Just do it what you're familiar with. Next, we're going to learn about calorimetry. This is a method that's going to allow us to measure the specific heat capacity of a substance. The technique uses a device called a calorimeter. You can find a picture of one on page 395 of the textbook. It consists of an insulated container that is filled with a liquid of a known specific heat capacity, usually water. There is a thermometer to measure the temperature of the liquid, and there is something that can be used to stir the liquid to make sure everything is evenly mixed. So basically, the hot object is placed into the water, and then the temperature change is observed on the thermometer. This calorimeter works based on the your textbook doesn't mention this, but there is something called equilibrium, which means all things equal. Now, as a general rule across all of nature, all forces seek equilibrium. So when you throw a ball, that ball wants to stop, right? Because forces are acting upon it to slow it down until it eventually comes to rest and it reaches static equilibrium. Whenever you take something hot out of a microwave, it immediately starts to cool down to reach room temperature. Same thing for when you remove a cold object and put it into a warmer area. The cold object begins to transfer heat with the atmosphere until all things reach the same temperature. All things equal, equilibrium. That is the basis that the calorimeter uses. So how it works is you place the object heated up to a known temperature into the liquid, and the object transfers heat out of itself into the liquid. So the temperature of the liquid is increasing, the temperature of the object is decreasing until they reach an equivalent temperature. And you can measure that change. This is how we can find the specific heat capacity of an object. And we're going to do an example that walks us through that. But before we can, let's look at equation 13.3. It's going to give us an important relationship between heat transfer and also introduce us to a concept. Currently, there is no perfect barrier to heat transfer in existence. We can put things in coolers, hoping to keep things cold longer, or thermoses, hoping to keep things hot longer, but eventually it's going to cool down because even though the container is well insulated, a perfect heat transfer, what am I saying? A perfect heat, the word is completely escaping me. You cannot stop heat from transferring completely. Currently, we don't have the technology to do that, which means that as the hot object is transferring heat into the water and the calorimeter are also transferring heat into each other. The calorimeter is going to be well insulated to avoid error in our experiments, but it's unavoidable. So we're going to draw a relationship of this heat transfer. The hot object, I'm going to truncate it at QO, is losing heat, so it has a negative sign, and it's going to come into equilibrium with the relatively colder liquid, QL, in addition to the relatively colder calorimeter, QC. So we're going to use this relationship in equation 13.2, but first there's another pink box on the page, 396, that we're going to read, In a calorimetry experiment, the temperature of the liquid and the calorimeter are always the same. In addition, the final temperature of the liquid, calorimeter, and object are all the same. So, initially, this temperature is different. These two are equal to each other. At the end, all three of these are equal. All three of these will hit equilibrium. So let's do example 3.2. I wish I could move. Can I move this? I'm not going to bother. Alright, I was going to move it up top to make more room, but this is fine. We are given that a 45.9 gram sample of an unknown metal. Let's go ahead and write this down as we go through. So the mass of the metal is going to be 45.9 grams, is heated to 89.7 degrees Celsius. So at the beginning of our experiment, our initial temperature, Ti, of the metal is going to be 89.7 degrees Celsius and dropped into a calorimeter that contains 150 grams of water. So we have a mass of the water, and that is 150 grams. The initial temperature of the water, Ti of water, is 25 degrees Celsius, room temperature. That's a pretty sloppy 5, I'm sorry. There we go, degrees Celsius. And by the end of the experiment, the temperature of all items, remember, because at the end of the experiment, the final temperature is all the same, the final temperature is equal to 26.9. Dropping our hot metal block into the calorimeter caused the total temperature to increase by 1.9 degrees. What is the specific heat of the metal? Now, we are told to ignore the heat absorbed by the calorimeter, which is convenient because that means the heat transfer in the calorimeter for this problem goes to 0, which means we don't have to worry about it. All that we're left with is the heat transfer in the object and the heat transfer of the water becoming equal. Now, we don't have enough information about the heat transfer of, well, we want to find this C, right? We want to find the specific heat. What's it called? I forget the name every time. The specific heat capacity. This is what we want right here. To get that, we need to find this, and to get this, we need to find this. And we have enough information to determine the specific heat capacity of the liquid, right? Because we're given an initial temperature of it. We know, we have memorized that the specific heat capacity of water is 4.184 joules per gram degree Celsius. And we have the mass of the water and the final temperature of the water. So we can find Q1 to find the first value of this relationship. So let's calculate Q. That's not a 1, I'm sorry, that's an L. I'm going to write a script L, the heat transfer of the liquid water. So with our equation, we can plug in the variables. Our mass of the liquid is 150 grams. It's going to be multiplied by our 4.184 joules per gram degree Celsius, multiplied by our temperature change. Remember, the temperature change is the final minus the initial. That means 26.9 minus The initial 25 is going to be our temperature change. This is 1.9. We're going to multiply all these together to get that the temperature change in the liquid, the heat transfer in the liquid, is 1200 joules. That is the heat transfer or energy transfer. Now, we know that at the end of the experiment, the object is going to have the same energy as the water, which means if our heat transfer in water is 1200, our heat transfer in the object is going to be negative 1200. That means our object is going to lose 1200 joules of heat. Now, we have the mass of our object, we have the temperature change that it undergoes, and we have a heat transfer now. We have the change in joules, so we can find the specific heat capacity. I've had this thing in front of my eyes the whole time, and I've forgotten so many times now. So let's do it. We're going to write in a negative, I was going to rearrange the equation first, but it doesn't matter. A negative 1200 joules, and set that equal to 45.9 grams, multiplied by our unknown variable C, multiplied by our change in temperature. The final temperature is 26.9, and the initial temperature, remember, we heated this thing up to 89.7 degrees Celsius. Now, doing the math here, we're going to subtract this, multiply this, and then divide the negative 1200 by these two, saying that quickly because you've all done this kind of math. We've been doing it, and we're going to find that our specific heat capacity will equal 0.42 joules per gram degrees Celsius. Now, I don't think the problem has you do this, but we can discover what element we dropped in, what metal we dropped in, by taking that value and going back to our table. So, looking over, we see that the two closest metals with a 0.42 specific heat capacity are nickel and iron. So we can be reasonably confident that the unknown metal is either nickel or iron. A little bit closer to nickel than it is iron. That takes us through comprehension checks 7 and 8. There's a little bit more reading before you get to those comprehension checks, and an experiment that we unfortunately cannot do at the moment. But we're going to stop there and pick up and do the rest of chapter 13 next week. So this week, you guys will have chapter 12 test sent to you. And you are going to do comprehension checks for chapter 13 through 8. And then we will pick up with example 13.3 and go to the end of the chapter next week, and then continue on to chapter 14. Have a good week.